Hello, Assalamualaikum, and a warm welcome to our lecturer. My name is Muhammad Faris M. Zulkifli, and my tree number is 191292494. So as we can see, this is experiment 5, the effect of different PID values. Okay, we use MATLAB command for PID analysis. So I will show about the graph. This is the effect of increasing parameter independently. Okay, we use this MATLAB, so we can see the graph. Okay, I will show you. Okay, now, okay, this is the graph without PID controller. The system settling time is 4.6. Rise time is 2.59. System peak amplitude greater than 0.499. Overshoot percentage 0. At time second greater than 7. Okay, this with the controller, with the PID controller. Okay, when KP is increased while KI and KD is constant. Okay, this is the graph as we can see. Okay, this is 3. KP increase while Ki and Kd still constant. So we can see this, and this is the result we get. So we can compare at the final value. Okay, the final value. Okay, this one we get only 0.9 0.5, but for system PID2 we get a final value 1. Yeah, also PID1 also get a final value of 1. Okay, we see when Ki is increased while Kp and Kd is constant. Okay, we can see here. Okay, and this is the response of TF when Ki increase. So this one is Kp increase, but this is Ki. Okay, this is the graph. We can see there's no much changes. Okay, just a little bit here changes in settling time, the rush time, and the second of peak amplitude. Okay, next, this one is KD is increased while KP and KI is constant also. You can see this is a little bit different. So the rush time of system for this one is 2.59 and the settling time 4.6. So this PID1, PID2, okay, we can see, and there's much different in the curve of the graph. So we can see here at the system PID1, peak amplitude is 1.07. Okay, and we see in peak amplitude for PID2 is only 1.02. Okay, the overshoot also has a little bit different. The overshoot is equals to 7.2%, while for PID2 equals to 1.9%. Okay, this is the table for without and with PID controllers. Okay, we can see this is transfer function, and this is the rise time overshoot and settling current for all the transfer function we put. Okay, for next task, we and we make a calculation for the task 4.1. Okay, as we get this result 1 over 1 s square plus 10s plus 20. Okay, the function. So we put this is without controller, PID controller. You can see the system rise time, the system settling time, and the system peak amplitude. Okay, overshoot at time second. Okay, this is with PID. This is much. We can see a much differences. Okay, for the graph of with PID controller, we can see a lot of changes here. Okay, this is for procedure 3.2. Okay, the procedure 3.2 we get rush time. We should this function is 1 over s square plus 10s plus 21. We get from calculation, so we get this from the graph above. The overshoot, the rise time, the settling time, steady state error. Okay, next, this is the from in this lab, PID controller is to read a sensor, then compute to read a sensor, then compute the desired actuator output by calculating proportional, integral, and derivative response, and summing those three components to compute the output. So the three component PID controller continuously calculate KP, KI, and KD. Okay, when KP increase, KI and KD remain constant, and the peak amplitude will boost as shown is in the graph. But when the peak amplitude is boost, the signal will have huge overshoot. So the settling time will take longer, as we see at the graph and the simulation, and then the transfer function without PID. So when KI is increased while the KP and KD remain constant, the signal will fast rise time like KP, but KI will have a small changes in overshoot. Also, the settling time of KI is shorter than KP, and the parameter of KI will eliminate the steady state error. Okay, and the derivative. Okay, now we the system graph with and without PID controller by using P, PI, PD, and PID is shown in the table above. So the proportional P equals to have a fast response time and minimize fluctuation, but does also not bring a system to desired set point. So the integral, which is I, will have contain small offset and return system to steady state, but the signal will have a slow response time. So we put in the derivative D. Will keep system at consistent settling and control processes with rapidly changing output, but requires combined use with another controller. So another controller, all the parameter P, I, D is shown in the graph above. So when both P and I increase, the P and I is proportional and the integral increase, so the signal will have fast rush time, but the value of overshoot are huge and the time taken to settling is long and infinite than other parameter. When PD controller is increased, the signal will have a fast rush time. So as we can see, fast settling time and the overshoot is also a zero, and the PD controller have a very good signal. Moreover, the PID controller have fast rise time and a high boost stable amplitude. The PID controller has zero overshoot. So now in conclusion, in this conclusion, I am able to learn how to use PID command in MATLAB. So we are able to analyze the effect when different, we can see P, I, integral, and the derivative D in a control system. The parameter PID have their own advantages and disadvantages in this control system. So each parameter has their own application. Some of them have their own characteristic. In general, the PID controller used for boost to the control system, compute their desired output, and continuously calculate an error value. Okay, that's all. Thank you.